Okay, let's see some examples of using these derivative rules now. And the first one I want to do is we're going to take f of x equals 3x to the fifth plus 2x to the minus first plus 3x to the minus 3/5. Okay. So now what's going on? Let's make that a plus 3/5 just to make things slightly more interesting in the long run. Okay, so I've got three pieces split up by addition. The linearity of derivatives say I can take the derivative of each piece. So if I want the derivative of all of this, I'm going to write out a lot of steps for these things just to make sure that we're using the rules properly. But the first thing we're going to do is we're going to use linearity of differentiation to get just down to the x to the powers inside the derivative. So the linearity says I can split this up. I can pull the 3 out, take the derivative of x to the fifth. I've got a plus sign, so I do that. And then I can pull the 2 out of the derivative. The x to the minus 1 stays inside the derivative. I can split off that plus sign, and that 3 can come outside. Derivative x to the 3/5. Okay, so I haven't taken any derivatives yet. I've just pulled off I've pulled off constants, and I've split up the derivative, and I'm going to do it in 3 parts. Now I'm going to start doing the derivatives using the power rule. So I've still got the 3 in the times, and the x to the fifth, the power rule says bring down the current exponent and replace it with an exponent that's 1 smaller. So I bring down the 5 and I replace it with an exponent that's exactly 1 smaller. 1 smaller than 5 is 4. Okay. Plus, I've got that 2. I get to use the power rule again here because I've got x to a power. I bring down the current exponent, which is a minus 1, and I replace it with 1 smaller. 1 smaller than minus 1 is minus 2. Okay, and then the last one, I've got 3. I get to bring down that current exponent, 3/5, and then I multiply by x to the power of 1 smaller. 1 smaller than 3/5 is going to be negative 2/5, right? 3/5 minus 1, 3/5 minus 5/5 ends up at negative 2/5. So there is my derivative. I can do some arithmetic on these constants out front, so I'm going to do that. I get 15 x to the fourth minus, because that minus 1 turns into a minus sign, so minus 2 x to the negative second plus 9/5 x to the negative 2/5. Okay. So in here, there was some interesting stuff happening. In algebra class, a lot of times you're told not to use negative exponents. Negative exponents are really, really handy when you get to calculus, though, because I can use the power rule on the negative exponents. If I had something that looked like, say, f of x equals 1 over x squared, I would have to use the quotient rule if I didn't want to use negative exponents. So we're going to write, and the quotient rule is sort of a lot. There was a lot more to it, right? It was the low d high minus high d low over the square of what's below. There's a lot more to that than just bring down the current exponent and replace it with something 1 smaller. So whenever I am able to use the power rule on something that's in the denominator here, I'm going to try and rewrite these things with a negative exponent. And then I can use the power rule instead of the quotient rule. They both get you to the same place at the end, but we'd like to use the easier thing if it was possible. So the derivative of, say, 1 over x squared, it's the same thing as the derivative of x to the minus second, which we write as, well, we bring down the current exponent and we reduce the exponent by 1, so that's minus 2 times x to the minus 3. Because minus 3 is 1 less than minus 2. Okay, so also make sure that you're moving left along the number line, right? Reducing by 1 moves you left 1 along the number line. So if you're on the negative side, you're moving farther to the left and go from negative 2 to negative 3. So this is negative 2 over x cubed, right? If I was going to write it without negative exponents again. So just be wary of those things. Okay, let's do one where I get to use the product rule now. So I've got y. I'm going to take 1 plus x times 1 plus 2x, and we're going to use the product rule on this. So I want, say, dy dx, and this is going to be, remember the product rule is the derivative of the first thing times the second plus the derivative of the second times the first. So I really like the big D notation because it sort of lets me tell myself that I still need to take derivatives at some point, and keep track of what I've already taken derivatives of in working through the problem and what I haven't taken derivatives of in the problem. I'll explain that a little bit more here in a second. So I want to take the derivative of this whole thing. It's a product of two functions. There's no just addition that I can split off or constant multiples I can split off, because there's this product that has to happen first, right? Orders of operations, products happen first, so there's no addition or constant multiplication that gets to be split off before the product happens. If there was like a plus something here, I could split that bit off and this bit off and split up the differentiation that way, but there's not, right? It's just the product is the first thing that happens. So the product rule says we take the first times the derivative of the second. So I'm just going to write out that I haven't taken the derivative of the second yet, but I'm going to write down that's the first times the derivative of the second plus the derivative of the first, which I'm not going to actually take yet, but I'm going to write down that I'm going to take the derivative of the first times the second. Okay, so that's why I like this notation here. It tells me I can still write down what I need to do yet. I've got it all split up and it's sort of organized, but I still need to take the derivative of this bit. I still need to take the derivative of this bit. So I've got 1 plus x. And I still need to take the derivative here. The derivative of this, I would split it up as the derivative of 1 plus 2 times the derivative of x, right? We're going to write down all the steps, but this is what I would still need to do. I can use linearity on this part now, but that means I need to include these big parentheses because I need to multiply 1 times x, or 1 plus x times all of that. Okay, plus, I'm going to use those big parentheses. I've got the derivative of 1 plus the derivative of x times 1 plus 2x. Okay, so I still need the derivative of 1. And the derivative of 1 is 0 because of the power rule. 1 plus x. So let me do that scratch work up here. The derivative of 1, well, if I think of that as the derivative of x to the 0, because x to the 0 is 1, right? That's the derivative of 0 times x to the minus 1, which we multiply by 0, I just get 0. This is 0. Okay, so if you're taking the derivative of a constant, right, any constant, you get 0. Because I can write this as, so if I wanted the derivative of c, that's c times the derivative of 1, and I know that that's 0, so this is going to be 0. Okay, so this is going to be 0 plus 2 times the derivative of x. X has an implicit derivative exponent of 1 there, so I bring down that exponent, and then I write down 1 less as the exponent, so I get 2 times 1 times x to the 0, which is just 2. We'll simplify that in a second. Plus the derivative of 1, we said was 0, plus the derivative of x, which is going to be 1 times x to the 0, and then I've got 1 plus 2x here. Okay, so I've got 1 plus x, that's 0, this is 2 times 2, plus 1, that's 0, and that's 1 times 1 plus 2x. I can expand and simplify this as 2 plus 2x plus 1 plus 2x is 3 plus 4x. Okay. So we can use the product rule. Alternatively, sometimes it's easier to do the expansion first. Right? I could have taken the derivative of 1 plus x times 1 plus 2x. I could have FOILed out this stuff, and I could have gotten the derivative of, that's a 1 plus a 3x plus a 2x squared. And then I use the power rules and everything. I get the derivative of 1 is 0 plus reducing the exponent on 1 by 1 gives me x to the 0, but I only have a 1 exponent to pull down, so that's a 3. Pulling down the 2 and multiplying gives me a 4. My new exponent is x to the first, so that is 3 plus 4x. We could have multiplied it out and done our differentiation that way. Either way is fine. Sometimes one of these ways will be quicker than the other. Like if I had a product of like 5 things here, I don't think I'd want to FOIL it out, but we could use that product rule and write it as a sum, or we could FOIL it all out and then do that. Either way, if you eventually simplify, you will get the same thing. Okay, let's see another example. Let's use one of those exponential rules, or a couple of them this time, and the product rule. So I've got y equals e to the x times 2 to the x minus 1. Okay, so I'm going to use the product rule. So I'm going to take the derivative of this, y prime, is equal to e to the x times the derivative of 2 to the x minus 1 plus the derivative of e to the x times 2 to the x minus 1. Okay, so this is equal to e to the x. The derivative of 2 to the x, we said, was the natural log of 2 times 2 to the x. The derivative of minus 1 is just a constant, so that's a plus 0. Plus the derivative of e to the x is just e to the x, because the natural log of e is 1. And I got 2 to the x minus 1 here. Okay, so there is our derivative of that, just the product rule and our exponential rules. The last one I want to do is, let's do a quotient rule example. So let's take, say, f of x is equal to e to the x minus x over e to the x plus x. Okay, so we're going to kind of combine some of these exponential rules and the quotient rule. So f prime is equal to, it's low d high, so e to the x plus x is the low, times the derivative of the top. And if I can think through this, the derivative of the top, the e to the x stays there. The derivative of minus x becomes minus 1. So that's low d high, right? Plus high d low, e to the x minus x, that's high, times the derivative of the bottom, e to the x plus 1. Okay, so that's high d low. And then it's over the square of what's below, so e to the x plus x squared. We can simplify this a little bit. We can expand these things, and let's do that just to kind of practice our algebra a little bit. I FOIL that first stuff. I get e to the 2x, right? E to the x times e to the x is e to the 2x, because you add exponents, right? And then I have a plus x e to the x, a minus e to the x, and a minus x. I am not happy with this plus sign here. Why am I not happy with this plus sign? Because the quotient rule says low d high minus high d low over square of what's below. Right? So this should be a minus sign. I'm going to make that a minus sign. Okay, so I've got this stuff, which was flying out the front, and minus this stuff. So I've got a, FOIL that out, e to the 2x. I've got a minus x e to the x. I've got a minus x and I've got a plus e to the x. I think that's all four of those terms. Okay. So let's see what happens here. We still have to put it over e to the x plus x squared. Okay, I've got an e to the 2x and an e to the 2x, right? Those guys are going to cancel because I've got the minus sign between them. So those guys cancel. I've got an x e to the x and a minus x e to the x, so that's going to become a plus 2 x e to the x. I've got a minus e to the x and a minus e to the x, so that's going to be a minus 2 e to the x. This minus x and this minus x are going to cancel, right? So those guys cancel. But I'm left with x e to the x minus e to the x and two of those, right? Two of them each. One here with that minus sign, one minus e to the x and another minus e to the x there. And then I've got e to the x plus x squared. So that simplified a little bit. And that was the last example I want to do. But you can use these rules in combination, right? You can use the power rule inside of the linear stuff. You can use the quotient rule and the power rules together. You can even use the quotient rule on top of a quotient rule if you had fractions of fractions. I would probably tell you to simplify the algebra first because the quotient rule gets pretty messy. So most of the time you want to simplify the algebra and then take the derivative. Some of the times, though, if you see a little trick on how to change what the problem looks like before you take the derivative so that it makes it easier, you can do that too. It just takes a lot of practice to get through some of these things, and you got to do lots and lots of examples to figure out, okay, when should I simplify, when should I sort of manipulate what it looks like before I take a derivative, that kind of thing. And we'll get plenty of practice of that this year. Okay, I will see you for section 3.4 next.